Hey, welcome back. In this lecture, we're going to orient the drone towards its own movement. And we're going to do this using math. So we're going to do a little bit of math just to figure out how much we need to rotate that drone so it looks like it's facing the player. And then we're going to use interpolation to make that turning a smooth movement so that it looks more natural as a drone can look. So let's get started. So I'd first like to show you the problem before we go working on the solution. Now, I think I'm done looking at this green floor, so I'm going to hit the P key to hide the nav mesh. It's still there. I just can't see it. Now, I'm going to overlap with our sphere from the side here so we can see the problem and see that our drone is not orienting in the correct direction. So I'm going to hit play, and I'm going to move over to the side of this sphere so that we're to the side, and I'm going to overlap. And we see that the drone sort of just slides in sideways. So for one, that's not great. We want our drone to be facing the correct direction. And for that matter, I see that with our drone selected, our x-axis direction is facing this way and the drone is facing the y. And in general, x means forward in Unreal Engine, which means our drone is not even facing forward in the first place. So we're going to come back into the blueprint and select our drone mesh and rotate it so that it's facing the X direction. So I'm going to hit the E key, and I have snapping on. I have 90-degree increments, so I can just snap 90 degrees to the right like so. And now our drone is facing the correct direction in the first place, but that still doesn't mean it's going to rotate to look at us. It's only going to stay facing the same direction unless we do something about it. So we're going to do that using the tick event. Now let's go back to the event graph. We've seen that the begin play event is called at the beginning of the actor's lifetime, whether it's the game starting because it was already in the level, or if we spawn an actor dynamically, that would be the beginning of the actor's life. But we want to use the tick event. So we're going to type tick and choose event tick. And this event is called every single frame of the game. And we have access to delta seconds, which is the amount of time since the last frame. Now, what I'd like to do in tick is orient our pawn towards the target, which means we need our goal actor here. So we're going to get goal actor, and we're going to be accessing this. Now, remember, our goal actor isn't even set until our character overlaps with our sphere component. Until that happens, this goal actor is empty. In fact, if we try to access this goal actor, let's take a look at that. Let's take goal actor. Let's say get object name. We'll call that function, and we'll attempt to print that to the screen with a print string node. So we know that goal actor isn't even set at the beginning of the game. So what happens if we try to play with this logic, trying to access goal actor? Let's hit play. And we see, first of all, that we're printing none to the screen. So we're accessing this empty variable that hasn't been set. We're getting the name, and we see that that name is none. So that's one thing. So we see none here for one. We're accessing this empty goal actor. We're getting the object name, and we're printing out its name, which is none. So that tells us right there that that variable is empty. Now I'm going to hit stop. And so what we should do before accessing goal actor is we should check to see if it's valid first. And we can do that with a node called isValid. Now, when you type isValid, you see an isValid function. This function simply returns a Boolean, which is true or false based on whether or not that variable is valid. Or there's another node, isValid, which has a question mark. And this one has an execution pin with an isValid and is not valid. So if this goal actor hasn't been set yet, then we get this is not valid executed. Otherwise, if it is valid, then we get the is valid executed. So we're going to use the is valid node to check to see if the goal actor is valid. In that case, we'll do something. Now, what we want to do is set our pawn rotation, and we need to know what to set that rotation to. Well, we have a goal actor, and the goal actor has its own location. We can access that by getting our goal actor and typing get actor location. And we also have our own location of this particular pawn that we're in. So I'm going to right click and type get actor location. So we have our own pawn rotation for the drone, and we have the actor location for the goal actor, which when it's valid, that's going to be us, the character. So we have two different locations, and we want to use these to find the correct rotation for the drone. We want the drone to rotate towards the goal actor. Well, Unreal Engine has a handy built-in function for this. It's called Find Look At Rotation. We can drag off of the drone pawn location and type Find Look At Rotation, and we see that it takes a start vector and it takes a target vector. The start vector is our drone pawn location. The target vector is the character location. So given a start and a target, this node will return the correct rotation that would orient the pawn so it's looking at the target. Pretty handy, right? So we can use this rotation, and if we want to use a rotator to set our pawn's rotation, we can use set actor rotation. Set actor rotation takes a rotator called new rotation, and we see that it takes a target, and by default that target is self, so we can leave that as self. Now, we only want to do this if goal actor is valid, so we're going to hook up is valid to set actor rotation. And now let's see how this works. And just to make this easier, I'm going to come up here to AI Move To, and I'm going to hold the Alt key and break this pin. So Alt left click will break that pin, so we'll never actually call AI Move To. That way we can see how this orientation logic works without worrying about getting blown up. So let's compile and save and play. Now I'm going to go over here and overlap, and look at that. It just snaps. It just looks at me instantly. It just kind of teleports its rotation, in a sense, toward me. And now that that goal actor is set to me, the character, you'll see that every single frame it's orienting toward me. So kind of creepy. Again, these drones are a little creepy, but they're actually pretty cool. So that is how we can orient the rotation. But we saw that that snap was sort of unnatural. And I'm talking about this. Pay attention. I'm about to overlap. Look at the drone. There, it snapped. It just really instantly snapped. It's almost like it gave itself whiplash looking at me. And I'd like to rotate that a little bit more slowly. And we can do that using interpolation. Now, interpolation is a technique used to change some value smoothly rather than just jerking into the target value like we saw with our drone pawn. When it comes to rotators, there's a special node called R-interp2, R standing for rotator. Now, R-interp2 takes a current rotator and a target rotator, as well as the value for delta time, which sort of seems to indicate that R-interp2 would be called with the tick event, since we have access to delta seconds, and it also takes an interp speed. So here's how it works. We pass in the current value of our rotator. That's going to be the drone pawn's current rotation. We then pass in a target value for the rotator, which is going to be the rotator that we calculated using Find Look At Rotation. Then we'll pass in delta time. We have access to that because we're using the tick function, and tick has delta seconds. And finally, we choose an interp speed, which determines how quickly our drone pawn will rotate toward the target. The exact math that R-interp2 does is it takes our current rotation and adds to it a value every frame. And that value is the target rotation minus the current rotation, in other words, the delta or difference between those two, multiplied by delta time times interp speed. Delta time is a very small value. It's the amount of seconds since the last frame, and frames are very, very short. And interp speed just scales that amount. And of course, target minus current keeps getting smaller and smaller as the current rotation approaches or gets closer to the target. So that's getting smaller and smaller each time, and that's why the change is smooth. So let's see how this works. In fact, you're going to see how it works because you're going to do this as your challenge. So use interpolation. Interpolate the rotation toward the target. and experiment with interp speeds. You're going to useRinterp2, passing in the drone's current rotation. You can use get actor rotation for that, and pass in the target, which we calculated using find look at rotation, and use the result from this Rinterp2 to set the actor rotation. Pause the video and give this a try. All right, so rather than setting the actor rotation directly, we want to interp. So I'm going to break that pin, and I'm going to right-click and type Rinterp2 and use Rinterp2. Now, we have a current, that's our pawn's current rotation, so we can right-click and type get actor rotation, and we can pass that right in. And we have a target, and that target is this, what we calculated using find look at rotation. So we're going to pass that in as the target. And we do need delta time, and we're using tick, so we can pass in delta seconds for delta time. Now for interp speed, we can experiment, but I'm going to pass in a value of 5 and see how that works. Now, none of this is going to work if we don't connect is valid to set actor rotation. And of course, we need to pass in a new rotation, and that's not going to be what we were passing in before. It's going to be the result of Rinterp2. So let's pass that in like that. And there we have it. Now, before we test this out, I really don't like my wires passing between and behind nodes, and I don't like my wires crossing much if I can help it. So I'm going to add a reroute to this wire that's passing through here. So I can double click on the wire and double click on it again, and that gives me some reroute nodes that I can use to make sure I see where these wires are going. All right, that looks good. Now I'm going to compile and hit play and see how this works. So I'm going to go up to the sphere. Let's pay attention to the drone. And look at that. It's even more creepy actually, because it just slowly looks at me like it knows I'm here, like it knows I was there already. So now we have our drone turning slowly to look at us. Excellent. Now, before we wrap this up, I'm going to go back and plug in AI Move To again and see how this looks with AI Move To active. Let's go ahead and overlap, and look at that. And of course, it came within the acceptance radius, and as I was backing away, I backed away fast enough that that inner sphere never collided with me. Now, if I go in and overlap, of course I get the explosion. So that's something we can change. We can go back to our AI Move To and set our acceptance radius to a value smaller than our explode sphere. Our explode sphere is at 133 or so, but we can make our acceptance radius a smaller value, like say 25. And that way, even if we're running away, it's not going to just stop chasing us until it's at least 25 units, which is much smaller than the sphere radius. So now we have smooth rotation. We have our drone turning towards us to look at us as soon as it knows we're there. And we're using interpolation to do this in a smooth manner, rather than jerking that rotation directly to look at us. So this is looking more natural. Great job. I'll see you soon.